All right, guys, it's time for some fun with math. And so today, I hope we have a, very short video. So we're going to talk about the final comparison test. So there's two comparison tests. Last time we talked about the comparison test, and this time we're going to talk about the limit comparison test. But first, let's just review real quickly. Remember our comparable series. So what's the idea with these comparable tests? The idea is basically we'll have one series that we do not know whether it converges or diverges, and we'll compare it, though, to a series that we do know converges or diverges. So just real quick, just a review. So remember, we have these what are called geometric series, and we understand these completely. They look like this: the sum n equals 0 to infinity of a times r to the n, and it'll be equal to a divided by 1 minus r, as long as your absolute value of r is less than 1. And then we also have these p series, and they look like this: the sum n equals 1 to infinity of 1 over n to the p, and these things converge if your p is bigger than 1, and they're going to diverge if p is less than or equal to 1. And again, p series we understand completely. And so what we want to do today is we want to do this limit comparison test. And the limit comparison test, unlike the comparison test, so the comparison test involves this inequality right here. And whenever a test or anything involves an inequality, the problem gets relatively, I don't want to say complicated or just difficult to do. But when it involves a limit, the problem just kind of almost solves itself. So with limits, like limits are like some like a power tool in calculus. Like once you can use a limit on it, boom, the problem just goes relatively quickly. So what do we have? We have two infinite series. So some of my a sub n's, some of my b sub n's, they are still positive series, which mean our a sub n's and b sub n's are basically positive. So they're bigger than 0, although they could equal 0, but they're positive series. And we have this condition. And so what's the condition? If you take the limit as n goes to infinity of a sub n divided by b sub n, so you take the ratio of the terms of those two series, if you get out a number c that's bigger than 0. So this limit exists and it's bigger than 0. So that's important, right? So this limit actually exists. So c is a number. It's not just infinity. Then what? Then we can conclude that both of these series do exactly the same thing. They either both converge or they're both going to diverge. All right, so let's just put this into action because it's actually pretty simple to do once you get the hang of it. So we're to use, and in this one, we should add here, we're to use the limit comparison test. All right, so limit comparison test to decide if the following series converge or diverge. All right, so let's take a look at this first one here. And it's a nice little sort of rational function with n on top and bottom. And so let's come down here and let's do this. And so when I see this problem, I'm thinking to myself, okay, well, how is this going to behave? It's basically going to behave like an n cubed over, I don't even care about that too, guys. It's just like an n cubed over n to the fifth. So it's going to behave like the sum of n equals 1 to infinity. It's kind of like these terms I just don't care about on top because n's getting really big eventually. And these terms on the bottom I don't care about because n's getting really big eventually. So it's basically just n cubed over n to the fifth, which is like a 1 over n squared. And 1 over n squared converges because it's a p series with p equal to what? So with p equal to 2, which is bigger than 1. And so I have a p series with p equal to 2, bigger than 1, so I know it converges. And so I'm going to compare it to that. So what I'm going to do is I'm going to run a limit on this thing. So I'm going to limit as n goes to infinity. It does not matter which one you put on top. I'll just put this one on top here. And so it's going to be this n cubed plus 2n minus 1, all divided by, and on the bottom I'll have 2n to the 5th plus 3n to the 4th plus n plus 7. And then I'm going to divide that all by this term right there of the other series, so 1 over n squared. And so let's see what happens here. So I'm going to get the limit as n goes to infinity. And on top, I'm just going to copy this down. So n cubed plus 2n minus 1, all divided by this 2n to the 5th plus 3n to the 4th plus n plus 7. And then I just multiply by this reciprocal. So that's n squared over 1. And so what's that going to be equal to? That's going to be equal to, I get a limit as n goes to infinity. And now I'm just going to multiply through by this n squared here. So this whole thing gets multiplied by n squared. So I'm going to get an n to the 5th plus multiply the 2n by n squared. So 2n cubed. And then minus multiply the 1 by n squared. So minus n squared. And then that's all divided by this 2n to the 5th plus 3n to the 4th plus n, and then plus a 7 right here. And now I can take that limit as n goes to infinity. So I'm going to cancel off all the lower degree terms on top. So I just have this n to the 5th left over. And on bottom, I'm going to cancel off all the lower degree terms. Just have the 2 to the n, 2 times n to the 5th left over. And remember, that's because I'm going to infinity. I'm allowed to do that. And so it's going to equal just the limit as n goes to infinity of n to the 5th, which is the term that dominates on top, and then 2 to the n to the 5th, which is the term that dominates on the bottom. And of course, now it's very clear what's going to happen. The n to the 5ths are going to cancel. And I guess I'll do one more step just for fun. So the limit as n goes to infinity of 1/2. And of course, that's equal to 1/2, which is bigger than 0. And so then what can I conclude? Well, I can conclude, therefore, my series, we'll call this, to give it a name, my series S. So therefore, S converges, and it converges because my P series converged up here, but it converges by the limit comparison test. And so that's how you run a limit comparison test. And it's actually, again, it's a pretty simple idea. It's like I have this series that I start with that I don't know what happens. I find a series that I do know what happens that kind of relates to it somehow, because then I'm going to run a limit on it. And what I look at is I look at the ratio of the terms. And if you think about it, the reason it works, it's basically saying is if you take the ratio of these terms, we wind up getting the same number out. So it's almost like each term, when you divide the two, right, you get the same number. So it means basically each term is like a multiple of the other term in the very end. So basically at the end, one series is simply a multiple of the other series. And so if one series converges, the other one does, or if the other one diverges, the other one does, and vice versa. And so that's why we can conclude here, basically they both converge or diverge. All right, so before we do any too deep of thinking, let's do it again. All right, so here's our next one. Again, we're going to use and this should say limit comparison test to determine if this series is going to converge or diverge. So I'm going to call it S. And again, what I do is I look at that sort of leading term. So I have like a square root of n basically divided by n. So over here, let me just write this square root of n divided by n, which is basically equal to a 1 over root n. And so I'm going to compare it to the series, the sum n equals 1 to infinity of 1 over root n, which actually diverges because it's a P series. And remember, P here is equal to 1/2. That's the square root, 1/2, which is less than or equal to 1. And so I'm thinking this series is going to diverge too. And to prove that, I'm going to run this limit comparison test on it. So I'll take the limit as n goes to infinity, and I'll just take this term here. So I'll write square root of n minus 1 divided by 3n, and then that's all going to be divided by, and I take this term here. So 1 over square root of n, which is equal to, and that's just the limit as n goes to infinity. And what we're going to do is we're just going to multiply by that reciprocal there. So we have square root of n minus 1 divided by 3n, and then times a root n over 1. And then we multiply through here, root n times root n is just an n. So we're going to get the limit as n goes to infinity of n minus root n. So we multiply 1 by root n, and then all divided by 3n. And basically, the same idea will work here. If you wanted to, you could probably L'Hopital this if you wanted to, but it's so much easier just to cross off that lower degree term there. And so then you have n over 3n, and then of course the n's are going to cancel. So if I go real slow here, you can see all my little thoughts. And so this is the limit as n goes to infinity of 1/3, which equals 1/3, which is bigger than 0. And so therefore, I can conclude S diverges, because up here, the series I'm comparing it to diverges by the limit comparison test. So I'm comparing the two series with a limit, basically. So that's why it's called the limit comparison test. All right, one last problem. And so now this one looks a little bit different. So now again, we're going to use the limit comparison test on this. And then notice on the bottom here, you have not a power of n, but an exponential. So it's more of like a geometric series. So my idea would be like, let's just kind of think, I think 1 over 2 to the n, or if you want 1/2 to the n equals, and you can do 1 to infinity. It doesn't matter if you do 1 to infinity or really 0 to infinity. It's still a geometric series. So I'll just do 1 because they started this at 1, but you could start at 0. It doesn't matter. And so this is a geometric series. And, oh, I should write converges, right? So it converges because it's a geometric series with your absolute value of r equal to 1/2, right, which is less than or equal to 1. Right, so the absolute value of r is less than or equal to 1, so it satisfies our conditions for convergence in a geometric series. And so now let's just see what happens here. And so we're going to run this limit as n goes to infinity. And again, you just take one term, and then we're just going to divide by the other term. So on top, I'll put the cosine of 1 over n over 2 to the n. And if you think a little deeply about this, all you're doing is saying, how do the terms compare when you take the ratio? And again, if you get a number out, basically it just says those two things are basically multiples of each other, which we'll make more precise here in a little bit. So then this is 1/2 to the n. And so what is this going to equal? Well, this is going to equal, when I multiply by that reciprocal, so limit as n goes to infinity of cosine of 1 over n divided by 2 to the n. And then times, and then what's the reciprocal of 1/2 to the n? Well, it's just going to be 2 over 1 to the n. And then notice this 2 to the n and this 2 to the n are going to cancel, and 1 to the n is just 1. And so this is going to be equal to the limit as n goes to infinity of cosine of 1 over n. And if you plug in infinity, what do we get? Cosine of 1 over infinity, which is really what? The cosine of 0, which is really, and again, I'm just kind of thinking here when I plug in that infinity, but cosine of 0 is 1, which is bigger than 0. And so what can we say? Therefore, right, that limit exists and it's bigger than 0. So therefore, what? So therefore, my series S, so my series S converges by the limit comparison test. All right. And it converges because what we're comparing to it actually converges too. Okay, so what's next? So the last thing I want to talk about here, guys, is why it actually works, right? So let's just kind of fill in the blanks here, because again, it's the explanation is almost obvious once you kind of see it. So why does a limit comparison test work the way that it does? So what we're going to do is we're going to suppose we have these two series here, the sum of these a sub n's and then the sum of these b sub n's here. And we'll assume that when you take the limit as n goes to infinity, you get out this number c, which is actually bigger than 0. Then for n very large, and so what do we mean by that? So when you take a limit, what does it actually mean? It means as n gets, in this case, it means as n gets bigger and bigger, this thing gets closer and closer to c, right? That's what a limit actually is. And so what we can say here then is for n very, very, very large, here's my c value, we can stuff this ratio between 2 times c and c over 2. Because remember, c is actually bigger than 0. And so this little ratio here lives somewhere inside this region. I don't know where, but I can stuff it inside of there, basically, is what I'm saying. And so here I can make this inequality. This is c over 2 is less than or equal to my a sub n divided by b sub n. And this is less than 2 times c, which doesn't seem like it should really matter, but it does when you clear out this denominator here, multiply both sides by b sub n. And so we'll get c over 2 times b sub n is less than or equal to that a sub n is less than or equal to c times b sub n. And now that we have this here, we can basically use the comparison test that we actually just did before, but we can just kind of reprove it. So what do we have now? We can actually rewrite this if we sum all these guys up, right? So just sum them all up, like put a sum here, add this guy, that inequality will hold, that inequality will hold, that inequality will hold. And so here, for the sum of the b sub n's, you can actually pull out the constant. So it's just c over 2 times that is less than equal to sum of the a sub n's, is less than equal to, and you just pull out the c here, c times the sum of the b sub n's. So what does that mean? So check it out. It just means that, hey, if you know that the a sub n's converge, so if you know these guys go to a number when you add them all up, it's going to force these guys to converge too, right? So the sum of these b sub n's are going to converge, and we can put the index on here, n equals 1 to infinity, because they lie below. If we know now the sum of the a sub n's diverge, so we know these things are going to infinity when you add them all up. Oh, what does that mean? That means these guys have to diverge also. Why? Because they just differ by a constant times the sum. So we know then the sum of the b sub n's, n equal 1 to infinity, must diverge too. And then we can play this the other way. If you have the sum of the b sub n's and you know those guys converge, what does that mean? Well, these guys are converging. So you add those all up and it's going to a number. And if you take all times c, it's still a number. That means these guys have to converge when you add them up because they lie below. And so then the sum, n equals 1 to infinity, of the a sub n's also converge. And then finally, if we take this last little statement here, the sum of these b sub n's, and if they diverge, it's going to imply what? Well, look, here's the sum of the b sub n's. If they diverge, it means they basically add up to infinity, because remember, these are positive sums, right? Positive series, basically. If this guy diverges, it's just multiplying it by a constant here, so it's also going to, still diverge, but it forces this guy to diverge, right? That sum to diverge, or that series to diverge. And so then you get the sum of n equal 1 to infinity of a sub n diverging too. And that's it. So that basically just says that the sum of a sub n's and sum of the b sub n's, so those two series, either both converge or diverge. They just basically do the same thing. And that's it, right? There are some small cases, subcases that I don't really push in this class, but just for fun, you can see here what would happen if this C winds up equaling infinity? Right, so if C equals infinity or C equals 0, some interesting things are basically going to happen on here. So if C is equal to infinity, what does that actually mean? Right? That means this A sub n over B sub n is going to infinity. So basically, the A sub n's are really, really big compared to the B sub n's. So if you know the sum of the B sub n's diverge, it's going to imply the sum of those A sub n's also diverge. So there's some little sub cases here you can kind of show for C when C is not actually a number, if it winds up being infinity. And then for C equal to 0, what does that mean? That means your little A sub n over B sub n's are going to go to 0. That means the B sub n's are actually a lot bigger than the A sub n's on top because it's going off to 0. So if you know the sum of the B sub n's then converge, it's going to imply the sum of those A sub n's also converge. And those are those little sub cases that I don't push real hard in this class, but I'd like to show you because you can get a little bit more out of this limit comparison test if you want to. Okay, well, that's it, guys.